third talk in active and driven soft matter. This one on self-propelled hard rods.
Okay, well, good morning, everybody. So, what I'd like to do today is show you how we can actually derive hydrodynamics equations using tools of statistical physics for a specific model system, and I choose what I like to think of as sort of a minimal, the simplest model I can think of, which is a model of self-propelled hard rods. So SP stands for self-propelled on the substrate, on the frictional substrate, and therefore two dimensions. We know that hard rods with simply exclude volume interaction form a matic phase, exhibit phase transition from an isotropic state to a matic state. So the question is, so I'm just going to take the same hard rod and assume that they have self-propelled, that is, that they have fixed speed v naught along the long axis at all times. I'll have many such rods. They interact with each other through excluded volume, and they experience friction with the substrate. So today, the medium will be completely passive, only provides friction. I will pretty much follow these notes, but I will, for a good part of the talk, use the blackboard, and then probably I'll use some slides when the equation starts getting a little bit longer. So the question is, what happens if I have self-propulsion to this type of system? Now, Chris Jasinski reminded us yesterday how you go about describing the dynamics of a many-body Hamiltonian system, start with Hamilton's equations, use Liouville's theorem, and so on. Is likely a different way of doing it, which is very useful when you're doing many-body systems, is actually to look, rather than looking at the evolution of the position and momentum of the particle, to actually look at the evolution of a distribution function in space. Similarly, what I'm interested in here is a system that has friction and noise. I will also have noise, by the way. I will choose noise that is Gaussian and delta correlated, white noise delta correlated in time, although the amplitude is not necessarily kBt. So when you have a system in the presence of noise, you can sort of use a similar idea in the sense that you can describe the dynamics at microscopic level with a set of coupled Langevin equations, so dynamics plus noise. And then Langevin equations are great as long as they're linear and preferably if there is no interaction, you can do everything with them. But as soon as you have nonlinearities of interaction, they become pretty difficult to deal with. So it is actually often more convenient to go from the description in terms of Langevin equation, which is sort of equivalent to the Hamilton equations of the Hamiltonian dynamics, to a description in terms of distribution functions, and actually obtain a hierarchy of equations, which is really a hierarchy of Fokker-Planck equations, for the noise average distribution functions, and then make approximations on those. For those of you who have heard of this, the hierarchy of Fokker-Planck equations is sort of the equivalent to something called the VBGKY hierarchy in Hamiltonian dynamics. Probably most of you don't know what the VBGKY hierarchy is, but since somebody mentioned the VBGK equation, I thought I will mention the VBGKY hierarchy. So that's the program for self-propelled hard rods. However, it's actually pretty difficult, and so the first thing I actually like to do is sort of step back and show you how this is done for one particle, not a rod, one point particle, if you like, in one dimension with nothing, with just friction really acting on it. So we have one particle in one dimension with noise and friction on the substrate. I'm going to write a spherical particle of radius A and mass m, although for the purpose of my talk, it really would be a point particle, other than I will write the friction into the radius. So I write a Langevin equation to describe the dynamics of this particle. And there is a frictional force. This is the velocity of the particle. Of course, the position is the derivative. It's an equation that relates to the position to the velocity. There is a friction, and there is some noise. The friction is just given by the usual Stokes expression. So imagine the substrate has viscosity eta, so the friction is just 6 pi eta A. And the noise is zero mean and is Gaussian, delta correlated with time, with a strength that I will call delta. If it was thermal noise, delta would be proportional to kBt. In fact, in equilibrium, the way you would determine delta is precisely by doing the following. You could actually solve this equation for V of t. In fact, I'll leave this to you as an exercise. It's a very simple, nice thing to do. Solve this equation for V of t with some specified initial condition, and calculate square V of t, and calculate the average, where the average means the average with this type of disorder. And now look at the long time limit of this V of t, and you find that is given by 2m squared delta divided by the square of the friction. If you are in thermal equilibrium, you want to require that a long time the system reaches equilibrium, and therefore this also has to equal what I will write as V square equilibrium, that is the average of V square of a Maxwell-Boltzmann distribution, which is just kBt over n. And so you will find the delta for a thermal system is essentially related to kBt times some friction factor and so on. So just do this and see. Now the other thing you can easily do from this one-dimensional Langevin equation, you can also calculate the mean square displacement, integrate things one more. So delta x of t is x of t minus x of 0, squaring, averages again. And that's another exercise that I will leave to you. And what you find is that this is given by 2m squared delta divided by zeta t minus m over zeta 1 minus e to the minus zeta t over n. So a long time, this is diffusive with the diffusion constant, which is given, this is square, with the diffusion constant, which is given by m squared delta divided zeta square. If you extract from here delta interval kBt, you cover that familiar Einstein relation between the diffusion constant and the friction. So this is all something we know very well. And physics, a linear Langevin equation, one particle, we can do lots of things with them. However, as I said, if we actually, what I really have in mind doing is doing many particles, interactions, and so on, and dealing with Langevin equation becomes difficult. So what I really want to do now is sort of show you how one transforms this one Langevin equation into something called a Fokker-Planck equation, which is an equation for the probability distribution. So the Langevin equation describes the stochastic process and which could also be described in terms of a distribution function f of x dt, and by the way, I will call this big X, okay? And I will put a hat on this distribution function for now. Distribution function represents the probability of finding the particles in the neighborhood of the phase point x. This is just one particle, so the phase space is very simple, s and time t. What I want to do is derive an equation for the noise average distribution function. So clearly, this depends on eta. I want to derive an equation for the noise average distribution function, and that equation is what is called Fokker-Planck equation. So to do that, it's actually, there are many ways of doing this, but a very simple way is to say, okay, first of all, this is probability distribution. Probability is normalized, it's conserved, must satisfy the following. And that means that f itself satisfies a continuity or a conservation law. And you can write that in the following way. So the time derivative of this f hat can be written, let's put it on this side, I'll have the derivative with respect to x, derivative of x with respect to t, times f hat. This must be equal to 0. This is a conservation law flux. This is the flux. Okay? And this big X means little x and little v, and that's my conservation law here. Now, what I want to do is essentially substitute the dynamics from the Langevin equation, which perhaps are right in terms of this big X. Yes?
Oh, no, sorry. That's the f hat there, and yeah.
This is f hat for now. Yeah. Okay. So let me rewrite the Langevin equation, and actually, I guess I would like to have x first. Let's do it this way. Let's see what I want to write. Okay, let's write it this way. And let's say that x is actually, let's use the momentum. So a little bit better, same thing. So let's rewrite this equation as dx over dt equal v plus eta, where x is xp, v clearly is p over m, and minus zeta v, and perhaps I will add a force, the derivative of a potential, just because I want to show you what happens if you actually keep track of a force on the particle. And clearly eta is, I don't have space to write, but eta is 0 and eta. There's no noise on the position, and there's only noise on the velocity. Okay, so if I do all of this, I then can insert that into this equation. And I'll get the following equation for this quantity f hat, still not noise average. Okay. And clearly, we need to keep in mind that f hat depends on eta, depends on the noise. Okay. So eventually what I want to do is derive an equation for the noise average quantity. Okay, but clearly, because that kind of depends on the noise, and I have the noise explicitly, I still really don't know how to do that. So in order to do that, I will do the following. I will kind of do this perturbatively in the noise, but then it turns out, and I will be able to show you that for Gaussian noise, which is data correlating in time, the perturbation theory really becomes exact. So let's solve this equation formally in the following way. Actually, let me, just for notation.
I'm sorry, I'm confused by little x and big X. Can you put a little bar over, like a bar over the big X and the bar over the big V as the vector of the velocities?
Okay.
So is that V by that F?
Well,
is that,
this is, okay, you want a bar as a vector?
Well, the V, I'm confused. Is that the V over here, this vector of momentum?
This is the vector.
Okay.
This is the vector noise. These are all vectors.
Okay.
If you like, well, I was trying to use the notation as in the off. This is big X. And I got rid of little v. I guess I should write this P over M. Okay. Let me just formally rewrite these. I define some operator. L is just this operator, whatever it is. And so these are all vectors now. I rewrite the equation this way, and now I will formally solve it, write the solution as E minus LT f of x and 0 minus integral from 0 to t ds e to the minus L t minus s, derivative with respect to x, eta of s, f of x and s. Okay? And now I insert these into the equation. This is a little bit algebra, but I thought it would be interesting to show you how this is done. And I finally get the following equation. Now I want to list some room because I'm eventually going to average this equation. So I get okay. I guess that's minus. Okay, so that's the equation I get. This is still an equation for the quantity which is not noise average. Now I want to noise average this equation. Just put brackets everywhere. Okay. And now, yes.
Is L a tensor or?
L in principle is it's an operator. It's not a tensor. It's an operator. It's the operator d over dx dot t. Okay. I just don't want to write that. I just wanted to write a little less. That's all it is. Okay. So now I want to average, and I do the average here. Well, the average on f hat is what I defined as the noise average distribution of that. I have to calculate the average of this quantity over here. And I am actually going to assume that the initial condition doesn't depend on the noise, which this term actually goes to 0. And the tricky part is to actually average this term. And what you actually want to do is sort of to keep iterating this. You do it perturbatively, that is, insert f again from the solution, and so on. And what you notice very, very quickly is that even the noise is Gaussian, only terms containing an even number of etas give you a non-zero result, and any term containing an odd number of eta will give you 0. So the first next iteration will give you a 0 here, and you have to go to 4 etas to get the first non-zero. Furthermore, because the noise is data correlated in time, and this is something I'll leave for you to actually prove, but because the noise is data correlated in time, and the noise here, we have two explicit terms, and then enters in f hat only at time x earlier than t, so there is a precise time ordering when you do this expansion, you can actually show that even if you do your entire perturbation theory, which no matter how many etas, the only, first of all, Gaussian noise can always, the averages can always be written as factor of second moment. The only factorization that will give you non-zero is the one where you factorize this with that. And everything else goes away. So you can actually show, and I encourage you to do it, that this average really equals the average of eta of t, eta of s, times the average of f.
Very quick question.
Yes.
Since f depends on the noise, so your argument about the even and odd powers would make sense if you were just averaging eta, but f also depends on the noise.
Yes.
So how do you still know that, like the average of eta f will be 0?
So imagine taking this and do a perturbation theory in the noise. So you keep iterating. I done it once. Now I take that and I insert it again. Okay, and I keep doing that.
Right.
So I generate terms that contain all kinds of powers, averages of all kinds of powers of the noise. The first thing I can immediately say is that averages that contain odd number of noises, those are 0 because the noise is Gaussian, and averages that contain even numbers can all be calculated by using Wick's theorem by factorizing them in pairs. Okay? Because the noise is data correlated in time and there is an ordering in time in here, you can actually show that all the terms vanish, all the factorization vanish with the exception of this one. And it's actually not very hard to show. Try the fourth one. Try to go to the one that contains 4 and you will see. Okay? And so essentially this term is really very simple because it becomes this, and then this correlation is just 2 delta t minus s, and so you can do the time integral immediately. Yes.
Yeah, I don't know if it, maybe for some people maybe we'll clarify it, but maybe not for others. But this is very similar to the way you treat potential in scattering theory, where you iterate to find a T-matrix. You
Yes.
iterate a certain good equation and then
That's
find
right.
the potential,
That's right.
and literally keep putting it back into the equation.
It's another way,
In
the
the
many
first
ways of
term-
deriving, the many ways of deriving from the Planck equation. I kind of like this one, but, it's, see, I mean, if you want to prove for yourself, you see that.
Well, the first term, if she wasn't averaging that first term at the Born approximation, but because she's averaging, she has to go to the second order. Eta is like the potential scattering potential. So now she has to go to second order in the scattering potential to beyond Born approximation because she's averaging, and the average of the potential is 0. Okay. But in principle, you have an infinite series.
I don't know how we can go. Okay, so anyway, after you do all of that, let me write down the Fokker-Planck equation here for the average quantity. So now for this F. And I will now write it out explicitly. That is, I'll go back to my original variable, P over M, and little x, which is the position. So the equation becomes minus P over M, derivative with respect to x of M, and this is something that may be actually familiar, derivative with respect to P. I write U prime of x, that is derivative of U with respect to x. Then I have flux friction times P over M. All of these acting on F. Can I see it here? I think so. Then delta, second derivative with respect to P of F. And this is the term that comes from here. Yes.
Are you assuming that the noise is small? Is a small quantity? So
No.
you can make that assumption?
What I'm assuming about the noise is that it's Gaussian and is delta correlated in time. By the way, I'm making no assumptions about the existence of a fluctuation dissipation theorem or approach to equilibrium or anything like that.
If you expand the infinite,
I do a perturbation theory in the noise, but I do it exactly. I resum all the terms.
Oh, you, okay.
Okay? That's really what I'm doing here. And this can be done in this case. Okay. So the point is I go from my Elijah equation to what's called the Fokker-Planck equation. For the noise average probability distribution. And for this, for one particle with U equals 0, well, actually it is not. you can use either one, and it's not particularly useful to use one or the other. Okay? But for many particles, it's actually useful to deal with distribution functions, and we will see. Now, so in fact, what I like to do next, so now this is what we want to keep in mind. I will erase all of this. I just want to give you an idea how this is derived. And you can find this in books, but it's not something that often people learn in class. Now, suppose now I had a system of interacting particles and some pairwise interaction among the particles. Then what I will start with is a set of coupled uneven equations. Say I label my particles by alpha. And I add, let me write it as a force. Well, actually, okay, let me write it as a derivative, write it this way, we see, well, a derivative of some kind of potential. Okay, then it's a derivative of some kind of potential. I guess it will be minus the derivative. Yes?
Yeah, sorry. It's a little bit hard to read the symbols from back here. Maybe I need glasses, or if you...
Maybe a little bigger.
Yeah, is anyone else having that, or is that just...
Yes, and I'm having trouble and I'm over here.
Oh, okay. Yeah, okay, thank you.
friction again. We have interaction. This means a derivative. And this is some state potential that depends on x alpha minus x beta. And we have noise. And now the noise generally depends on alpha. It's still Gaussian. So now I have these labels, alpha and beta. And different particles have uncorrelated noise. So now I want to go from a description of many coupled Langevin equations into again a description in terms of distribution function. The distribution function for all the particles will be sort of phase-space distribution function. But I can also define a set of reduced distribution functions. That is, I can define distribution function, I'll call it f sub s of, now I introduce the big x again, maybe x1 up to x sub s, as the phase-space probability of finding particle 1 at x1 through particle s, test sub s, regardless of all the other n minus s particles. And I can define a one particle reduced distribution, two particle, and so on. This is a standard way of dealing with many-mode systems. And so instead of deriving a single equation, like a Liouville equation would be in Hamiltonian dynamics, for the phase-space distribution, I can derive an infinite hierarchy of equations for the 1, 2, 3, 4 particle reduced distribution functions. They are equivalent, and they are equivalently empty in the sense that there's nothing you can do with them unless you make some approximation. So in this case, what we actually do is we derive a hierarchy of Fokker-Planck equations for the noise average reduced distribution functions. And I'd like to write down just the first one. I think I wrote it down here in the notes, which will look the following. So we give an equation for the one particle distribution, and maybe I just use one actually for notation here. It would be minus v1 derivative with respect to x1 plus, so it has some of the one particle terms that you have in that equation as well. And then we'll have a term that comes from the interaction. And the interaction contributes to the force, which is essentially, so here you have one of the terms that come into the force. So you can see where this will come from. Okay, so the equation for the one particle distribution couples to the two particle distribution, the equation for the two particle couples to the three particle, and you have an infinite hierarchy, and unless you make some approximations, you won't be able to proceed. So we're going to make a pretty one often makes a pretty drastic approximation. So these are some of the approximations made so far. We're going to make one more. We're going to assume we have, let's say, a low density, or more precisely, we neglect correlations, and we're going to assume that the two-particle distribution is just the product of two one-particle distribution. And once you do that, you have a closed equation for the one particle distribution, which are still you are generally not able to solve, but at least there's a closed equation that you can try to do something with. Okay? Now finally, one of the simplest ways, there are many ways to do it. There are books written on Fokker-Planck equations. Yes?
I was curious, in what sort of limit and what regime is this sort of approximation valid?
Low density, because it really depends a bit on the system you're dealing with. If you write, so far I guess I'm really talking about a gas of particles, so it would be an ideal gas where the distance between the particle is large compared to the range of the interaction, and if I'm eventually interested here in things like hard interactions that will be produced by their size.
So ultimately, like the probability of a three-body like collision.
Right. So I'm neglecting, but I'm doing more than neglecting three-body collisions. I am also assuming that really the correlations are, so it's lowest order. So in expansion in the density times the square of some length that determines the range of the strength of the interaction. And the square of some length because I'm in 2 dimensions, if I'm working 3 dimensions. Yes.
And why does particle 1 couple only with 2 in the...
I'm assuming pairwise interactions. Okay, I mean, that's just my assumption.
Right, but shouldn't that be, say, V13, V14?
Integrating all.
I'm integrating overall the position and the momentum of particle 2.
Okay, sorry.
So that's summing over there. Okay. So one of the simplest ways of starting to do something with an equation of this kind is to take moments. Okay, do you have a question? Okay. And so let me introduce the first 2 moments, and you can actually take an infinite number of moments, and then you don't have to solve it. So I'm going to truncate. I'm going to do sort of like a moment expansion and then truncate it. But actually, I'm going to state it in a much simpler way. I'm going to introduce the first 2 moments of the probability distribution, and what the velocity or momentum moment. And what I mean is the following. So let me take the probability distribution, which is a function of x, p, and t, integrated over the momentum, and that will be the concentration of particles. I'm going to use c instead of rho for density essentially today. And I take the first momentum moment, and actually, let me actually divide it by m. You'll see why, mostly because I'm doing a number density here rather than a mass density. And so this will be a curve. Okay? So I will take the first 2 moments of this equation and get equations for these quantities, and then see what I can do. Remember, we want to keep in back our mind that my goal here is to derive hydrodynamic equations, which are equations only for the conserved fields in this case. And in this case, we really only have one, the concentration, because the momentum is not conserved. We have a substrate that takes momentum away from the system. And also, there are going to be equations that apply at large length scales. I'm going to be doing a gradient expansion, essentially. So that's my goal. That's why I'm going in this direction. So the equation for the 2 moments are written here in this note. Well, for the concentration, clearly, it's very simple. The only term that is a contribution is this one. Everything else vanishes because you iterate by part, and everything else vanishes. And just a continuity equation that says that the rate of change of the density is the gradient of the curve.
At this stage, these are all point particles.
These are all point particles, yes. I mean, it's much more complicated for us, but in fact, I won't do a lot of it for us. I want to show you how it works for point particles. And then I take the next moment to get an equation for the current. And here it's a little bit tricky. Well, this term is really easy. So let's do that first. I have a missing factor of mass in the notes, I should say. So there is a minus zeta over m j. That's what you get when you write it a little better. So there is a missing factor of m in the note in this first term, actually. Then I have, well, that term is, okay. Okay, this term, what you're going to end up with is the average of v squared over momentum, right? The momentum average of v squared. And I have erased the result here, but the momentum average of v squared is essentially delta, the strength of the noise, if you remember. So this term will give the term that I'm about to write down now, and if you put in all the right factors, you get m over zeta times delta, derivative with respect to x1 of c of x1. So this is 1. I need to keep track of the symbols because I'm going to be integrating over the 2. And then, this term actually goes away. I have the term coming from the force, which gives me a minus. Again, I have a mass, 1 over mass missing in the notes. I can write it this way. as integral over dx2, derivative with respect of x1. The potential, I'm assuming, depends only on x, and it actually depends on x1 minus x2. And then I have c of x1t and c of x2t. Okay? So these are written in your notes. Sometimes it's a little hard to redo things. Here you have a conservation law and an equation for the momentum. Now, the next step is that you want to recognize that, as I said, you're interested in hydrodynamics. You're really interested in only an equation for the conserved density that is C. And in long time scales, you're interested actually in time scale long compared to this time scale. So this is actually a frequency. So in time scale long compared to n over theta. Time scale theta large compared to 1 over the friction. The system is over then. This term dominates that one. So we are going to assume, if you like, we are assuming that velocities relax much more quickly to equilibrium than position. We neglect this compared to that. We solve this equation, we put it back in here, and we get a closed equation for the concentration, which is almost, in this simple case, our hydrodynamic equation. It's actually what's called the Small-Chomsky equation. And let me write it down for you. And now I will drop the label x1 because I have only one. No, I still have, sorry, not yet. Okay, derivative of respect to time of c of x1. I get d, second derivative with respect of x1 of c, and d is determined by the noise. This comes from this term, and is determined by the noise according to the expression I wrote down before when I wrote the expression for the mean square displacement. And then I have plus 1 over friction, derivative with respect to x1, integral over x2, derivative with respect of x1 of dx12. I guess at this point I will erase the assumptions that we have made. And c of x1 and time, and I'm going to write time explicitly, and c of x2. So that's what's called the Small-Chomsky equation.
In the concentration you're taking two derivatives of, that's of x1?
The second derivative with respect to x1.
Of c
yes.
of
x1. This is c of x1, and that's c of x2. Okay, if I don't tell you what it is, it's c of x1. And d, I can rewrite it here, was equal to n squared delta divided zeta squared. Yes?
Can I ask you to explain why the first term is zero for the current V1 dash x1 F1?
Oh, it's not zero. It gives you this. This gives you this. This is the variance, the square of the average of the square of the velocity. Because you multiply with another velocity and averaging over velocity. You multiply by momentum and averaging over momentum.
But you've done the averaging, right?
I've done the average over noise. Now I'm taking velocity moments. Okay? And I am assuming, so what I calculated before was the average of the square of the velocity over the noise. And it is, now I'm assuming that the average of the square of the velocity over the noise average distribution is the same as what I calculated before. Okay? So, okay, so we are almost there. This is almost a hydrodynamic equation. Not quite. If you like, it's a non-local hydrodynamic equation. The last thing we need to put in is the statement that we are interested in length scale large, basically compared to any other length in the system, if you like, and in particular, and we're going to be doing an expansion of the gradient. There is some length scale in here, which is essentially the range of the potential. For example, interaction, which is characterized as the range of the potential. And so what I can do is, let me just take this term. And let me do a change of variable. Let me rewrite it as 1 over zeta, derivative with respect of x1. So I'm writing it explicitly since people don't seem to like my sort of other derivatives. Okay, so sorry. What I want to do, I first want to do an integral by parts. So I bring this derivative over the c, okay, and I get a minus sign. And then I do a change of variable. I let x prime equal to x1, 2. So what I end up with here, so now I have integral over x prime of v of x prime times derivative with respect of x1 of c of x1 times c of x1 plus x prime.
Christina, your integral is over x2, right?
Yes.
So what do you mean by integration by parts?
Yep.
Okay. This is a function
Right, it's a function of difference.
of x1. I might decide, in fact, I think I missed the sign. This is a function of x1 minus x2. So the derivative of x1 of the function of x1 minus x2 is minus the derivative with respect to x2 of the function of x1 minus x2. So in fact, actually, I think it remains a plus because I have two signs. Okay, so that's what I do there. And now I expand this in the gradient. I assume that x prime is controlled by the range of the potential, and I'm interested in length scale large compared to that. And so I expand this. The first term is c of x1. The second contains a derivative of c of x1, and so on. So now this, if you like, I write it c of x1 plus x prime, derivative with respect of x1, c of x1, plus more terms. And if I only retain the lowest order term, which already contains 1 and 2 derivatives over here, eventually the equation I end up with has the following form. The diffusion equation, which is what you expect for a hydrodynamic equation for this really simple problem. It's a diffusion equation with a diffusion constant, which is the bare single particle one, plus I can also calculate corrections. I can specify some interactions. I can calculate corrections due to interactions. So I have a systematic way of calculating the parameters in the hydrodynamic equation. Of course, they're both model dependent. They will depend on what kind of potential I put in. And of course, they are valid at low density, because I made a low density approximation. Yes?
So the bare diffusion constant is the one that comes from the substrate, right?
Yes, in this case, yes.
And the corrections
absolutely.
are there.
The correction comes from interactions.
Particle.
The corrections come from interactions. Okay? But I have a systematic way of doing this. And of course, this is a very, very simple problem. It's just point particle the substrate. And now I think I'm going to go to the, the slides, because otherwise I don't think. So did we actually switch this off? What happened?
You're just on standby.
Now I want to do this for rods, and I want to do it for self-propelled rods. Now, this is going to be quite a bit more complicated for a number of reasons. Yeah, I don't know. Well, so this is going to be, to go to rods is more complicated for many, many reasons. First of all, just one more minute. A rod has both translational and rotational degrees of freedom. So here is my rod. It's one of them. I will describe the rod in terms of the position R alpha of its center of mass with respect to some fixed coordinate system. And the unit vector mu alpha determines its orientation, which in 2 dimensions is really just one angle, theta. Okay? Still, I have the dynamics involve coupled translation and rotational degrees of freedom. I'll have a Langevin equation for the translational and the rotational degrees of freedom, and they're coupled because the diffusion of the rod is anisotropic. The rod diffuses faster along the direction of the axis than transverse to the axis. And so this gives you a coupling in the dynamics. I don't know why I cannot go back to my previous slide. Okay, let me just. Okay. And here are the equations for the Langevin equations for the rod. So at the top you have the Langevin equation. So I have the coupling of a translation and rotational degrees of freedom. I have the self-propulsion. And in addition, I have interactions which I will treat as hardcore interactions. So here is the Langevin equations for the translation degrees of freedom. Here is the self-propulsion. Here is the friction, which is now a tensor, because it's different along the direction of the long axis of the rod and then transverse to it. I have interactions, which are written this way. I'll tell you why in a minute. And I have noise. And then I have an equation for the rotational degree of freedom. I didn't write that there, but omega alpha is the rate of change of the angle of the rod. It's the angular velocity of the rod. The interactions are written in this funny form in terms of something called the temperature, because hardcore collisions are instantaneous. You cannot really describe them as derivative potential. So you describe them as a rule that changes the velocity before the collision to the velocity after the collision. And this is well known for hard spheres, much more complicated for hard rods, but doable. And here is the noise prescribed here. Now I've written the delta instead of something that I call an effective temperature. Yes.
Rods are, two-dimensional.
This is 2 dimensions. Yes, this is all in 2 dimensions. I don't know why my thing doesn't go.
Excuse me, this effective temperature, how do you define it?
I've written delta as kBTA. It's just a definition, really. I've written the noise as kBTA. I don't know why I cannot get this thing to go forward. Okay. What's that? You know what?
Restart it.
Well, I don't have time to restart. Can people see this? Yeah? No?
You can blow it out. You can zoom out, zoom plots a little. No.
What's that? All right, so if I zoom, so it's much more complicated to do what I was describing here for our rods. But let me just tell you what happens if I do it. I get a Smoluchowski equation, which, first of all, the blue terms are due to self-propulsion. So let's ignore the blue terms for a minute, and let's just look at the Smoluchowski equation for hard rods. Those are all the black terms. What we have diffusion again, but now we have rotational diffusion. dr, which is really just a frequency. And we have translational diffusion, d parallel and d perp, which is anisotropic because rods diffuse faster along the length than transverse to the length. And we have interaction, which is really just excluded volume interaction. And it determines a force on the rod and a torque on the rod. And it can be written in terms of excluded volume potential along Zager, which mu1 cross mu2 is the sine of the angle between the unit vector that tells you the direction of the 2 rods. So sine of that angle times L squared, if L is the length of the rod, is the excluded volume, which is in 2 dimensions. So it's the excluded volume times the probability of finding another rod at contact. There is a condition here, which is that the 2 rods be at contact. Psi 1, 2 is the size of these vectors that go from the center of each rod to the point of contact. So the collision is pretty complicated for rods, and there is a lot of, but it's something that we know how to do. When you introduce self-propulsions, you find several new things. First of all, an obvious one, there is mass convection along the direction of self-propulsion. The rods are self-propelled at the speed v naught, so we get that term, that's pretty obvious. But we also can calculate this diffusion constant, you can calculate the effect of the various interactions and so on, and so also the effect of self-propulsion. And we find an enhancement of longitudinal diffusion, this ds, where this ds actually goes like v naught squared. And this is simply because a self-propelled rod is sort of undergoing something called a persistent random walk, and so its longitudinal diffusion is enhanced by a term proportional to v naught squared. And then there are it was written there, sorry, I missed it. And then there are contributions to the torque and the force that the rod exerts on each other, because essentially there is an additional longitudinal momentum exchange by self-propelled rod in addition to that exchange just by hard rod. That gives you these two contributions over here, which really, this is just supposed to show you it's pretty messy and complicated, but again you can calculate it, so you get an expression for this Langevin equation. And in order to actually do this, really, there is another assumption you have to make. Essentially, as soon as you have self-propulsion of the rod, you're really coupling clearly velocity with orientational degrees of freedom. And so there are some correlations between velocity and orientational degrees of freedom that have essentially been neglected here. And that's the main approximation that has been made.
Are you assuming that the rod switches direction randomly?
I'm assuming that the rod switches its direction only when it collides with another rod through a hard interaction.
But there's noise too.
Sorry?
But there's noise that changes the direction.
There is also noise. Yes, it can also change the direction because there is noise, so it's also there is also rotational diffusion.
I meant forward and backward.
That's rotational diffusion. No, it's not just they're not just forward and backward collision. It's conservation of momentum and energy, and describe your collision in gory detail. So it's actually through hard body collisions of rod that is incorporated. Okay.
So I'm to understand that you're motivating this towards trying to understand like swarming E. coli. Mm-hmm. Right? So do you have in E. coli undergoes a bias random walk, so do you have that bias in here?
Yeah, the self-propulsion of the rod.
Well, so how do you define the self-propulsion of the rod for E. coli, which is it proportional to the concentration gradient for some attractant or repulsant?
Actually, what I have in mind here is not so much E. coli, because E. coli really swims in the fluid. I have in mind more vibrated granular rod, or an experiment called an active motility assay, which is an experiment where people coat a plane with myosin motors and then put actin on it, and the myosin kicks the actin along, and you can actually watch this actin move along. And the low density of actin, you really do see an enhancement of longitudinal diffusions, just like the one. And then in that case, the naught square is proportional to the concentration of ATP, essentially, the fuel that drives the motors. And you do see an enhancement of longitudinal diffusion of the type of V naught square. And now people in Munich, in Andreas Bausch group, are doing experiments at high concentration of actin, and they're seeing some of the effects that I might not have time to show you, but I'll try to show at least one that you can get out of it.
So this is a bad model for like E. coli chemotaxis.
Well, now there's nothing about chemotaxis here. I'm looking, but my goal here is to try to understand the effects of physical interactions. Chemotaxis is outside. I just want to see what physical interaction do, and hardcore is the simplest physical interaction we can think of. Yes?
A small question is V0. Would this be the terminal speed if there are no interactions?
V0 is the given prescribed speed of each one of these rods. I just define the model. I don't know what makes them move. I don't care. I'm just saying these rods have a speed V0.
So they always move with the speed?
They always move with the speed V0. The speed is always replenished even after a collision. Okay? What changes is the direction, but the speed, they always move at the speed V0. Okay? So from the Luchowski equation I showed you there, I actually want to do two model dynamics, what I did here. So I will sort of take moment And I need really a few quantities because I want to consider the possibility of ordering of this rod. So I need the concentration, which I call rho, sorry, I don't know. And I need the polarization vector, and I need the nematic alignment tensor. And I derive equations for this quantity, which are pretty complicated, and they're given on the next page of your notes. I'm not sure I really want to go through them. But let me just tell you what happens. In the simplest of cases, let me take these hydrodynamic equations. I'm not going to show them here, but you have them in your notes. They're complicated. They're equations for rho, polarization, and Q, and they look very complicated. Let's first of all just ask what happens in a homogeneous steady state. Let's throw away all the gradient terms, and let's ask, can self-propulsion, we know extruded volume can give you a nematic state. Can self-propulsion give you a polar state? And actually the answer is no. So the hydrodynamic equations neglecting all gradient terms are given by this. And in this approximation, I don't really get an isotropic nematic transition, but I get the signal of the transition by the fact that the decay of fluctuations in the change in sign of the coefficient of Q indicates that when rho is larger than rho in, the fluctuations in the alignment tensor will become unstable, and that's the signature of the nematic transition. To actually really calculate the transition, I need to keep terms of order Q cube, and once Gonzaga did that, so you could actually do that. But so the steady state solution of these equations are, of course, an isotropic state of constant density and 0 P and Q. No polar state, P is always 0 in a uniform system, and there is a nematic state, and what happens is that actually self-propulsion enhances nematic order by lowering the isotropic nematic transition according to this formula given here. And this is actually an effect that has been seen.
You can zoom in and just not do that.
Oh, no, you don't want to do that. Sorry?
Cristina, you can zoom in right there with a plus.
Yeah, but it doesn't, somehow it's stuck, it doesn't let me
No,
go.
no.
Zoom
in
saying
right
I
there
can use
more.
these and
then use
zoom in.
those. But if you zoom in and then you get rid of the outline on the right.
Click sidebar. Up. Sidebar. Yeah, good.
Right.
So I never use this. I decided to use this thing, I don't know why. And
What is it?
So can people see that? That would be a little bit strange. These are actually numerical simulations of the motility and active motility assay. As I said, active motility assay are easy to do at low density of active. They've been done for a long time. They're only now people are starting to do them at high density. This is a numerical simulation, and they see precisely this enhancement of pneumatic order due to the motor protein. As I said, Andreas Bausch and this group are actually doing this now in real motility assay and try to construct this phase diagram. Let me just take one more minute. One interesting thing I can do also with these hydrodynamic equations, I establish what are the homogeneous states of the system, then I can look at the hydrodynamic modes in the system. Let's suppose we look at the simplest of states, the isotropic state. Homogeneous density, 0 polarization, 0 alignment tensor. Let me draw the alignment tensor for simplicity. Let's look at the dynamics of fluctuations in this isotropic state. And you can go to Fourier space to get the mode. And what you find, and actually this is done on the previous page, but I'm not going to show it here because I don't have time. I just want to show you the result for a minute. What you find is that there is a critical value of the self-propulsion speed, which is given here, above which the system supports sound-like waves in the range of wave vector. Now this is surprising. Why is it surprising? This is an over-dense collection of rods. Density fluctuations decay via diffusion. They don't propagate. Okay? Now, in the limit k going to 0 strictly, it's always diffusive, the system. But there is a broad range of k where these, the system actually supports propagating waves, sound-like waves, and these have actually been seen in this motility assay. We think that is they do see this kind of propagating waves of density, and we're trying to see if we can interpret the velocity at which these density waves move. We can relate it to the ATP concentration in the system in some way that is an analog to our V0 here.
So simply use a picture that explains the emergence of this propagating symbols.
Essentially, this happens when, so you can define two characteristic length scales. Let's call it a self-propulsion length scale and the diffusion length scale, which is the length scale that the central mass of the rod will move in a time 1 over dr. Dr is the rate at which rotational diffusion takes place. Okay? So you define these two length scales. So this actually occurs where the self-propulsion length scale increases diffusion. So the density fluctuation doesn't have time to diffuse away, it moves forward first. Okay. And I think I'll have to stop here, but the point is, and then you can look at the stability, you actually can show that the nematic state is unstable, as you would actually also expect. The systems generally do not form bulk stable order state. So let me just try and summarize what you can get out of this model. Which in my mind, as I said, is a minimal model of self-propelled system. You get no bulk polar state, which is kind of disappointing, but we'll see that it's very hard to get a bulk polar state. And experiments actually don't usually see it. They see long-range, large correlated regions, but no bulk state. You get enhancement of nematic order, enhancement of longitudinal diffusion, these sound waves, and you can also look at the correlation length of polarizations and see how they ladder. They get pretty large. And several of these things actually can be correlated for now at least qualitatively with things that have been seen in experiments, either in vibrated rods or in this motility assessment. So tomorrow I will actually try to describe to you a sort of a richer model that actually incorporates the fluid flow and may be relevant for things like E. coli and bacterial suspension in general. So sorry if I went a little bit over and for this. So, thank you. And the Fokker plan derivation is taken from this book, which I think is a very nice book. To look just a couple of chapters there. And this is actually work that was mostly done by my postdoc, Aparna Bhaskaran, and we have written some papers on it. All
right, are there any questions?
Yes.
Two questions. If you use the formula to study the pneumatic phase, I would have thought that the pneumatic phase would mean that it's of high density. And so to what extent when you assume there's no second order correlation is valid when you are studying the pneumatic phase. And the second question is, you said there's no bulk polar state. I got the Bicek model of you and Toner's paper.
Yeah. So first question is, you're absolutely right. I'm assuming low density, and then I kind of try to apply these things at high density. So the point is that if you want to derive quadratic equations using this kind of method, you're stuck. You have to at some point assume low density. You will derive equations where the structure of the equations, because these equations are valid on basic symmetry principles, which I was trying to explain in the first two lectures. So if you do things correctly, the structure of the equations you will derive will be correct. It's correct whether you are at high or low density. This method allows you to calculate the parameters, but the parameters are valid only at low density. So yes, if I actually put in my parameter values, I am pushing it, I agree. However, I personally think this kind of derivations, it's very useful to go along with the phenomenological symmetry-based kind of theory, because it does give you a physical feeling for what these things mean and what, in principle, you could, if you really want to work very hard. And when I was young, I did some of these, but not anymore. You could try to calculate density corrections to these things and free body and so on, but that's certainly not for us. Anyway. Now your second question, yes. Okay, so actually this is precisely, the Bicek model is precisely what motivated us. Bicek model is the following: you have point particles with a fixed velocity, with a fixed speed, and there is some rules that describe the dynamics, and the rules are that at every time step, I look at my neighbors within some radius, I align myself I change my direction by aligning myself with the neighbors, and I go on. And this model predicts a transition of still not settled order, let's say, from a state which is disordered and not moving to a state which is polar, but is disordered and moving. But this model puts in the ordering by hand. The alignment is put in by hand. I look at my neighbors and I align with my neighbors. The question we wanted to ask was precisely, can the simplest of physical interactions, hardcore collisions, give you that kind of alignment? And the answer is no. And the answer is not no. This is complicated to get into. But the answer is not just no alone, density, as a matter of fact. And so it's, so you have to look somewhere else. But next we did was to look at hydrodynamic interactions. And actually we found that the answer is no again, as a matter of fact. At least it cannot give you a bulk homogeneous polar state, which is what theorists would like to call, that's what theorists are looking for. It gives you large correlated regions, but in the limit, in the bulk limit, there is never a P is always zero. Okay, so that's, Any other questions? Yes?
I suppose I'll ask a question which maybe you'll address tomorrow. What type of interactions do you have to put in to get, for example, form sensing behavior and that sort of thing in collab?
Maybe you have to put in, people usually talk about chemotaxis, they talk about, so maybe you have to put in something like that. That would be to be an external symmetry breaking. This is something from the outside. Okay, and that's certainly,
so you could treat that like an applied magnetic field.
Or some kind of biochemical signaling among the...
And you could treat that as like an effective magnetic field breaking symmetry and
I don't think people have looked at it quite that way, but it could be measured. But, so,
that sort of phenomenology could give you this polar flow that you're looking for?
Yes, those kind of things can give it to you, yes. But, I wanted, coming from physics point of view, I wanted to ask whether physical interactions can give you this. And it's okay, the answer is no, I just wanted to know the answer, whether it was yes or no. So far we haven't found one that can actually give it to you, just on the basis of physics. But if you look at, people have done simulations. People have done simulations with self-propelled hard rock, simulating the Langevin equation. They do not see a macroscopic polar state, even for periodic boundary conditions. They see large correlated regions, but there are always fluctuations. So it's not, the system is not uniform. Now, in the Bichet model, yes, you do. You do see let's call it bulk correlated moving region. But in models that start out of interactions like this, you actually don't. So it's not so, I guess, it's not surprising in retrospect.
I just add a comment. I think if you really talk about chemotaxis, then you definitely need another concentration field for the chemical agent.
Yeah.
But the precise mechanism of that, as far as I understand, as an outsider, people are still fighting over. So, this is a very contentious and active research field at this point.
Yeah.
Maybe someone in the audience can correct me, but I don't think there's agreement in the literature often.
Well, there's been a lot of work there which is mostly based on coupled diffusion equations, yes. And you get all kinds of patterns. By the way, you can certainly get the polar state here. You could all start with a channel, require the boundary, the system to be polarized at the boundary, and then if the channel is small enough compared to some landscape which actually grows like V0 square again, then your system will be polarized. You can do that. But if you really look at bulk, usually we ask the questions about phase transition in the limit of infinite system, well then it is zero. So, maybe we work much too hard for something like this, but that's what people do.
Any other questions? Not? We have a break until